Yeah, small school. I tell my father-in-law who's a professor there, it's a junior university. Leyland Stanford Junior. Anyway, as you can tell from my background, I'm in the semiconductor industry. How many people out there are in the semiconductor industry, design chips? Oh, great, there are a few of them. I'm glad to hear that. One of the problems with IoT is knowing who's going to be in the audience and how you pitch the thing correctly for the audience. So I'm going to try to keep this at a high level. I'm not going to talk about how many atoms thick my oxides have to be and all of that kind of stuff. Try the other direction. Okay. So just a little bit about QuickLogic. We're really involved in the business of maximizing battery life for people, and that was good in consumer electronics. It's going to be better in IoT. We're about putting more intelligence into devices local, so we're not in the big cloud stuff. We're trying to push intelligence out to the very edge, which has a number of power benefits and so on and so forth. Whoops, wrong direction. So when I started thinking about this, so I've been playing around with this area for a couple of years now, and one of the guys I talked to is kind of interesting, he works in the consumer electronics company. He's the director of advanced materials. So I asked him, what do you do as director of advanced materials? Do you come up with new materials? And he said, no, actually that's a bad conception. What I do is I look at old materials, things that have been around for a while, and I work out what's changed in the world that might make them useful today in a different way. And the example he gave of that was carbon fiber. So carbon fiber came up in the 80s probably. It was used in aerospace. It was very expensive. It was very hard to use. It has some great properties, but you wouldn't consider it for consumer electronics. So he said, so if you look, what's happened now is 30 years has rolled by, and even though it's expensive, people have been driving down the cost and so on and so forth, and suddenly you realize that no, the cost and the ability to use it has gotten to the place where it could be used in consumer electronics. So instead of just saying, oh, carbon fiber too expensive, don't think about it, let's start thinking about where we could use it. And that's what they started doing, and now you see carbon fiber showing up in various consumer electronics kind of things and other consumer things. So I thought, well, that's an interesting point of view. Let's think about that in terms of electronics. What's been happening in electronics? What are we built in that we know that's true, that's no longer true? So I've been knocking around in this industry for 40 years now, and for 40 years it's all been about smaller geometries, higher performance, more integration, more software. That's what makes this business grow, right? That's what made semiconductor great. But now we have to ask, well, is that still true, or is it not true, or is there an alternative way? And I think a new path is emerging. It's been emerging for a couple of years, and you can see people starting to understand that this new path is there, and it's directly tied into the different needs of IoT from cell phones. If you think about cell phones, very big processors, very big audience for them. IoT, probably small things, lots of small things, and diverse things. So what about that? So here we go back. This is 4004 from 1975, I think. And it's grown all the way up. And you can see, I mean, this is what our industry talks about, right? More and more, how many transistors can we jam into a chip? So that's about using Moore's law to put more into a chip, well-named law there. But you can actually look at it a slightly different way, and we'll come back to that in a second. So this old way was what people in semiconductor business used to call up and to the right. You know, we're going to get more and more bigger and better and faster. So if you look here, you have a whole range of processors. So this is the ARM's point of view. You have capability, the Cortex things, M0, M3, M4, and then you get the R series and the A series. And if you look from a software perspective, because the other thing that's changed in this 40 years is it used to be people did hardware. Now they mostly do software, and there's lots of reasons for that, flexibility and so on. But for software perspective, now I have a CPU for every need. If I have a little bit of compute power, I use a Cortex. If I need a lot of compute power, I use an A15 core. I run a bigger CPU. I run the clock faster. The 4004 had a 12 megahertz clock, something like that. No, a couple hundred kilohertz clock, right? Now we moved up to gigahertz. You put more memory on it. Software always likes more memory. If you need even more performance, you go to multiple CPUs. You see a lot of that around. If you still don't have enough performance, you add a hardware accelerator. And that's actually what drove the FPGA business, which is the business I've been in for the past bunch of years. When you can't get enough performance out of that big A-class processor, what do? You put a big Xilinx or an Altera FPGA out there. And you've been seeing they go in base stations and all of these kind of things. They've been going into servers more recently, and we'll talk about that in a minute. But that's been the old way of doing things. More, bigger, faster. That's what we talk about. So now we come back to what I think is kind of the interesting part is what's changing now. So everybody talks about this. Most costs are changing. So when I started in this business, most costs were about $50,000. So you could build an integrated circuit for about the same cost as building a PC board. It's kind of interesting. It costs you about $50,000 to get the most for the PC board and get your prototypes. That's definitely not true today. We're talking millions of dollars on most cost. And the thing most people don't talk about is because it's millions of dollars of most cost, you don't want to make a mistake. So now you're going to spend more millions of dollars on verification. So when I look at my product development cycles, essentially the design finishes, and then there's at least 3 months of verification, layout, and all of that kind of stuff, which is going to cost me several $1 million. Then I buy my MOS, then I wait another 3 months, I get my chip back, and then I go through a verification cycle on that. So it's no longer possible to do a small spin. You know, if I spend a month spinning something in RTL, then I'm going to spend 6 months implementing this thing and deploying it, and that's not a very good return on my money. The other thing that's happening is fragmented markets. For the past decade or so, we've been driven by the cell phone. There's, you know, everybody has a cell phone, just about, maybe have two. And that's a fairly homogeneous market. There's maybe 5 suppliers that supply almost all of that market. So that means if you're Qualcomm or somebody, you can build a chip and you're going to sell literally hundreds of millions of that chip. That justifies spending all of these millions of dollars building that chip. I don't think that's going to happen in IoT. I don't think there's any single market that has that capacity to deploy, you know, 50 million units in a year of any one thing. I think it's going to be, you know, a bunch of stuff in washing machines, a bunch of stuff in refrigerators, a bunch of stuff in that. And each one of those things is slightly different, which means now you're going after a fragmented market. The other thing about this market is it doesn't turn over as quickly. So most people turn over their cell phones. It used to be 18 months. It's now moving out to about 24 months, right? Housing stock doesn't turn over that fast. If you want to make smart homes, they turn over maybe 2% a year in the US, maybe 1% a year in Europe. So you're in a retrofit business. You're not in a whole new business coming in. We'll talk about the role of software. And then another thing that's happening, everybody's observed this, is that there is this consolidation happening in the semiconductor business. So what does consolidation mean? It means that we're moving maybe from a phase of innovation to a phase of scale of company, and that means you want to own more of the BOM, right? You want to own more of the device that's going into the system. That's easier to do in a mature market, except of course IoT is not mature yet, so there's a challenge there. And so what that means is you'd like to drive more of the decision making. So let's explore those 4 aspects of this in a little more detail. So MOS costs, as I said, in the 80s, MOS were very cheap, and reciprocally, transistors were very expensive. So you would do a lot of work to minimize the number of transistors you had. And even though FPGAs have been around for a long time, FPGA gates are more expensive than ASIC gates. And that's another interesting little anecdote here, is that a lot of people have been in the FPGA business over the past. There's about 50 companies, maybe 52 companies have done FPGA, big guys like Intel and IBM and so on. In the late 80s, a lot of people were looking at embedding FPGA. You had Adaptive Silicon that was bought by LSI Logic. IBM had offerings in there. And one of those companies said to everybody that, you know, FPGA gates are about 10 times as expensive as ASIC gates. Well, I now know what to call that. We call that fake news, because in reality, it was 50x. But the trouble is, once one of your competitors has gone out and said it's 10x, if you say 50x, nobody even talks to you, right? So there's a conspiracy of silence around that. So these FPGA gates are prohibitively expensive, at least they were back then. Now you think, oh, if it's 50x, there's no way somebody is going to use programmable logic. I mean, that's just too big of a price differential. But I have an example here of price differential. This costs maybe $1. If you wouldn't water your lawn with this. The reason why you wouldn't water your lawn with this is if you go to the tap there and open up the water fountain, that water costs you about $10 for a ton of water, which is much, much, much more economical than this. So the reason why these guys get away with selling such expensive water is it's in a convenient size, and I don't buy a lot of it. So what we need to do when we look at gates, FPGA gates, is we need to look at what's a usable amount of gates and what does that usable amount of gates cost. So I've plotted here in the blue curve what about 15,000 gates worth of FPGA logic would cost you. So in 65 nanometers, I think it costs you about 10 cents. So if you're an MCU company and you're selling your MCU for, maybe $1.50 or something like that, the die itself probably costs like 60 cents. Adding 10 cents onto that, that's a pretty big increment. You might do it or you might not. If you move down to 40 nanometers, it drops down to 5 cents. So now you're talking about a 10% adder to do this. That's starting to look like that's the risk that people will be willing to take. And if you move down to 22 nanometers, well, now your cost drops below about 3 cents to do this. And that's a perfectly reasonable thing to do on an MCU for some flexibility. So that's one of the changes that I think is coming along that's changing the economics, especially of FPGA or embedded FPGA. So let's talk about fragmented changing markets. So here's one of the Beecham research, I think. IoT it really isn't a market. It's hundreds of markets, right? It's an umbrella term. The good news is there's a lot of opportunity. These are all new markets. The bad news is it makes it very difficult to tell what these markets need. So you need some flexibility. And because they tend to be smaller markets, so again, when I build a product for the phone market, I can maybe plan on getting 50 million units from one sale or 10 million units from one sale. In the IoT market, it's looking more like 1 million units is a big deal. 100,000 is more typical. So that means I need to do multiple SKUs. And then how am I going to do that? Well, HBR says you need to follow a build, test, learn process because this market, we don't know what it needs. So you're going to build something, you're going to put it out in the market, you're going to trial it, you're going to find you didn't quite get it right, and you're going to have to change it. Where does that push you? And even worse, components must be amenable to still unidentified future products. So how do you do that in a silicon world? So let's talk about the build, test, learn. FPGA companies like Xilinx, Altera, and ourselves, they've been doing this for 30 years. It used to be called burn and learn. So you just build the things, you try them out, they don't work, you tweak them to get there. It's very easy to do with an FPGA or an embedded FPGA. It's really hard and expensive to do that with silicon, especially when you $1 million pop every time you want to make a spin, as we talked about. The other thing, for those of you in the semiconductor industry, is it goes against the semiconductor culture, which is do it right the first time. When you're building $30 or $40 million devices, you spend a lot of time making sure that darn thing is perfect, and I mean perfect, and it's 1 billion transistors. Getting that perfect is really difficult. So there's a whole culture built about doing that. And if you go into that culture and you say, I want you to just take a guess and go ahead and do this thing, that's anathema to them, and it's very hard to get them to change direction in that regard. And that is hurting the adoption of embedded FPGA. We're just not used to that. And then there's this issue of still unidentified future products. So in our company, we build products that are SoCs that have Cortex processors in them and have FPGA in them. And the pushback I always get is, well, what goes in that FPGA? How do I design something when I don't know what you're going to use it for? And that's the unidentified future product design. And our corporate culture is not set up to do that. What we have found, though, is if we put a piece of FPGA in there, even though we don't know what it's used for, even though we don't know how big to make it, because we don't know how many gates your problem will take when it comes up, what happens in practice is we run into some customer who's often got some strange need that we didn't think about beforehand, and that customer says, ooh, can you use your FPGA to solve that need? And then all of a sudden, the problem turns around from what do I need to solve that need as to how do I fit that need in that FPGA? And that's a different mindset than the normal engineering mindset, which is what do I need to solve my problem. This is what the D-School guys called crank up the constraints. So once you have this constraint, I've got 15,000 gates worth of logic and I got this problem. How do I fit it in the 15,000 gates? You'll find the engineers get quite creative, and you'll be amazed at what you can do in 15,000 gates when that's your only way of getting it done. So you can be amazed at what can be done with a small amount of programmable logic. I think one of the reasons for that is because it's kind of low risk at that point. If you're building an ASIC and you're building like a SD controller in it, you go, I'm not sure what people are going to do, so I'm going to put in every feature they might need because I want to have everything they need. Whereas with programmable logic, you flip the problem around and you say, what exactly does this customer need? I'm going to strip out everything they don't need. And if you think about that for a minute, that's a lesson we're learning from the software business, the agile stuff. Don't put too much stuff in there. Just cut to the core of it, get it out there, see what happens, fix it as you go forward. Now, software. I alluded to this before. You can use hardware to solve two problems. One is CPU too slow, the other is CPU too power hungry. Actually, this is the same problem. The CPU too slow problem is that actually to make it run at the speed you need to, it takes too much power and the silicon melts. So they go to hardware to solve the too power hungry problem. So this is a case of I got a power budget and I want to get more performance. That's the traditional model. The new model I'm contending is that I have a performance and I want to reduce the power, and I can use hardware to do that. It's the flip side of the coin. So we can flip around the curve in the IoT space and we can say, look, capability, battery life, high capability, low battery life, less capability, better battery life. And when you really want long battery life, you've got to push into programmable or hardware or programmable logic. Hardware is best. It's even lower power than FPGA, but of course it doesn't have the flexibility. And just to give you an example of that, we worked with a company called Runtastic. They build a watch. It's an analog watch. Actually, it's a stepper motor that steps around. So it looks like an analog watch, but they wanted to add pedometry function and sleep function, all the stuff you find in the classical fitness monitors. So we programmed all of the pedometer and everything into an FPGA, and they get 6 months of battery life out of their coin cell battery. And I defy you to do that with an M0 or any other CPU. So the other thing that McKinsey talks about is components must be small enough to be embedded in various different things. Earbuds and so on are a particularly important thing. But even in the bigger things like watches, the trade-off people have is, every component takes up volume. And you have a choice. Do I use that volume to make my industrial design more sleek, which people like? Or do I use that volume to put a bigger battery in so I get better battery life? So what you have today is most of these watch kind of things or bands have some kind of CPU in there, and there's very often an FPGA sitting beside it to do something else. If you can combine that FPGA with the original MCU or stuff, you're reducing volume, which lets you do all of these good things that you actually want to do. So there's another reason for adding FPGA into conventional devices. And then we talk about this wave of consolidation. Every extra component you have in a system brings another vendor into the equation. And all of these vendors are competing for the dollars that are going to go into this device. And different bundlings may go in different directions. So there's more and more pressure now to own. The more complete solution you can get, the more of the BOM you own, the more likely you are to be in the lead position. So if you think about a cell phone, the first thing they talk about is what AP am I going to use? Is that going to come from Qualcomm or MTK or somebody else? They don't really spend a lot of time at the beginning thinking about whose microphone they're going to use. They get down there. But in the wearables, a lot of these MCUs start to become the main thing in the system, and the more complete you can have it, the less chance there is for somebody else to sneak in and win that socket away from you. So again, having this completeness of solution, especially when you recognize that many times there's an FPGA sitting beside there, sucking it in there will help you lock down more of the market share. So my summary on this is what's changed is transistor costs have gotten low enough that you can have a useful amount of programmable logic for a few cents if you incorporate it in your device. Most costs are high enough that adding a few cents is a good idea. So I figured out the break even, maybe 50 million units is now 22 nanometers. 50 million units is a break even between a most cost and adding 2 cents to a device. Rapidly evolving market favors first time to market solutions. Now, if we think about IoT, it is about giving features to customers. It tends to be software driven. So can you get into that market quickly and lock down that customer before someone else gets in there? You want your silicon to support that. And we believe you can do that better with some programmable logic in there. Fragmented market combined with high market cost favors flexible solutions. So again, if I'm building a cell phone today, I know exactly what that CPU has to do. I can lock it down and deliver the whole value. I can't do that in IoT today. So I want some flexibility to address a need that I didn't think of. When performance is critical, hardware beats software. So sometimes you need to build little hardware accelerators that can speed things up. Logic's good for that. Programmable logic's good for that. Sometimes when power is critical, hardware beats software. Good examples of that are a lot of phones actually, one of the issues is monitoring all of the buttons on them. You really don't want to have a processor sitting there polling all the buttons trying to say, oh, did someone push a button? A little piece of hardware will do that a lot better. And the other thing you have to remember is when I said there were 50, maybe 52 FPGA companies, of which maybe 5 are still around, what happened to the other 45? It wasn't technology, it was tools. It was the software that's wrapped around it. So as you look at an embedded FPGA, you've got to look at the tools and how you're going to deploy those tools. So in that regard, we just recently announced that we have released first of our we license the IP. So we build product and we license the IP that we actually use in our product for other people to use. Other companies do this, license the IP. We think we're well positioned because we actually use it in our own products for things. And we're working our way through the different foundries and different processes. Personally, I really like working with Global on 22FDX because I think from a product point of view, that's going to be a fabulous process for IoT. It's got the MRAM you need, so you don't have to have flash. It's got good economics, and it's got good power and performance capabilities. So that's the end. Thank you.
We have something to present.
Yeah, because of your, again, thank you for sponsorship.
You're welcome.
For the conference.